Hi everyone, welcome to today's session on use different models. The idea here is simple yet powerful. Leveraging multiple models can provide unique perspectives and deeper insights into complex problems, which a single model might miss. Take, for instance, the decision to buy a home, a significant life choice. You would not just look at your monthly financial commitments, you'd also evaluate the location, community, and future growth potential. If all these different models point in the same direction, your confidence in making a right choice increases. Industries are applying this principle too. In automotive design, for example, engineers use computational fluid dynamics to optimize the aerodynamics of a vehicle, while finite element analysis ensures the vehicle's structural integrity under stress. Similarly, in the energy sector, predictive models forecast future demands, and spatial models decide where to best place wind turbines or solar panels for maximum efficiency. In the retail world, using multiple forecasting models helps predict consumer demand more accurately, allowing business to manage inventory better and reduce losses. Today, let's dive deeper with a practical example. We will explore how different models are used in analyzing and controlling a wind turbine. We will start with a detailed gearbox model to identify potential failure scenarios through vibration analysis. Then, we will simplify our approach with a model focusing on controlling the turbine's speed. By the end of this session, you should be able to appreciate the versatility and necessity of using multiple models to enhance decision making, predict outcomes more accurately, and understand systems more comprehensively. Let's get started. Hi Vedat.
Hi, Ankit. Hello, everyone.
Yes, so what are we going to look today?
Yeah, today what we have a wind turbine, you named.
Yes. So as we said, Vedat, like the concept of use different models, right? And before we start on the wind turbine, like what do we mean when we say use different models? Because there are as I see it, there are two different ways of seeing it, right? When I say use different models, let's say you have a single modeling objective. Like for
Right,
instance, let's say what is the power output from the wind turbine, right? And then to predict that, you can have different types of models. You can have a physical model where you have a distribution of a wind and get the power output, or let's say you have a historical data and based on that you can get a power output, or perhaps there are other models which are looking at a single modeling objective,
right. I mean,
right?
yeah, for to me, it looks like what your objective is. In a case, you might be interested in, let's say, a gearbox vibrations,
Hmm.
where you can just figure out where the vibrations are coming from, etc.
Hmm.
Or in a larger scale, as you rightly said, we might have a wind data, and we are just looking for whether that location is a good candidate for building up a this type of wind turbine, how much energy we can harvest to see such details. So two different objectives we are here.
Right.
We have here.
So the first one was you have one problem that you want to solve and you are using multiple models to solve one problem, and in the other case, depending on the problem, you are using different models, right?
Right.
Yes.
And at the end of the day, we can still name both of them wind turbine model, right?
Yes. So one has to be very clear when you create a model what your modeling objective is, and what are your assumptions, and yeah, and list those things in the model. Right. So with that, I thought for today, for the wind turbine, we would show three different examples. One would be a very detailed model whose objective is, let's say, you are a windmill, wind turbine manufacturer, and you want to create a new wind turbine model, and you want to analyze what are the stresses inside a gearbox. You want to visualize and analyze the stresses, right? That is
Right.
one model that I want to discuss today. And the second one is, let's say you are not a wind turbine manufacturer, but you are a kind of a grid operator, right? And when you are a grid operator, you just want a wind input, what is the power output and how much energy you can sell to the grid, right?
Right.
And the third model, which we will discuss using our system dynamics principle that we have learned so far, is, for instance, like people like you and me who are just interested, let's say, in a particular location, how much power is available and how much power I can just extract. I'm not
Right.
interested in how much money I will make by selling it to grid, but we want a general understanding of what is the potential for the wind power, right? So there are three different uh, use cases that we will try to see today, and each one having a different objective,
Yeah.
right?
Also, before getting deep dive into the model, it would be nice to give some heads up. So here, uh, in the first case, as Ankit rightly said, we will look into details what we have in this wind turbine, and then we will use other domain, which is electrical from the mechanical. You remember for the DC motor, to see how much energy we can generate, and at last, we know that uh, it is not so common knowledge that everyone knows about DC motor, because not everyone here is electrical engineer. So, but we use so far the business simulation library, right? So we will just try to create an equivalent model by using the business simulation library to see how the dynamics look alike.
Right,
So don't get afraid when we, yeah, when we start showing the details about this gearbox.
right.
Yep.
Okay, Vedat. So with that, let's get started with our first model, which is on modeling a high fidelity, like a very detailed wind turbine gearbox model. Um, and okay, so in order to use this model, we have to load the rotating machinery.sma. So let me open up system modeler. I already have the rotating machinery SMA loaded, and you would have received the rotating machinery SMA in the download folder. So let me just, uh, yes. So you would have received the rotating machinery SMA. You can just drag in the SMA into system modeler, and it would automatically install it for you, right? And Vedat here is has developed or has been involved in the rotating machinery library. So Vedat, before we look into the specific example, like what is this rotating machinery library, and just can you give me a briefly like what
Right,
this library
right,
does and who is the target audience for this library?
right. The target audience, I will say that assume that you are developing any rotating machinery such as pumps, turbines, or wind turbines. So you can steam turbines, any turbines you can name it, or Jeff cut rotor using systems. You can just employ this library to see what is happening in your system. You might have some certain constraints to test. We have so many components to design those systems like bearings, we have gears. Other than that, we have contact dynamics. Also, we have like almost 30 examples, 30 different use case where you can just check. For instance, Ankit is looking for wind turbine gearbox. Over there, you see the parameters. You can just tune those parameters according to your own specific design and test how the dynamics look like, how the stresses, how the indentations
Right.
uh, in a gearbox.
So Vedat, I will like to pause you there because you're going into details now,
Right,
and I think
right,
a lot of our audience perhaps may not be in the mechanical engineering domain side. Even I'm a mechanical engineer, but I have not gone into the mechanical design of things. So what you're trying to say is, if someone is involved in the engineering design of this rotating machinery or someone is involved in vibration analysis of rotating
Right.
systems, perhaps it is more relevant to that audience.
Right. It
Right?
is. It is. Yeah. It is really high fidelity uh, models. I mean, it has really high fidelity models. So
Yes. And
yeah,
with that, uh, can you just tell me, like, if I simulate this model, how much time it would take me to get the result?
I will say it will take roughly 2 hours to get your results.
2 hours?
Yeah.
Come on.
Yeah. So, but I mean, instead of running a finite element analysis where you have all the details, all the stress distribution, you are just running this and see where those interactions happening, where the potential failure happening. So you can just run this and easily test your conceptual designs and see the results whether your design suffice or not.
Okay.
So
So with that, as you said, this simulation takes a lot of time to simulate. And let's say I have a model which is very time consuming. I simulate my model, and I want to share my results with some third party, right?
right,
With your friends, colleagues, or students. I want to share my results. So how can I share my simulation results without having them wait for 2 hours, and then
right.
making easily access those results? How can we do
Yeah,
that?
yeah, that is when the SME comes into picture. So
Yes.
which you already share.
Yes, and I also wanted to make it clear, it's a very big file, 370 MB file, so we do not expect everyone to load it. The objective of this first session, where we go into the detailed model, is to show you some of the one way that you can model high fidelity models, right? So, and in this session, as we said, we will have three different ways of modeling different things related to the wind turbine. So, so Vedat, we will look into how to create SME, perhaps in a different model
Right,
later on. Let's start by just using an SME. So here I have my wind turbine gearbox.sme file. In order to open it, either I can double click and it will open in Simulation Center, or I can just drag it to my Simulation Center here, right?
right. So
And
yeah.
yes,
Also, Ankit, can you tell us so how we created this? I mean, what type of file is that?
yes, okay. So let me give you a
Is,
quick.
is, is that
Mhm,
something we create by using System Modeler or Mathematica?
mhm. So Vedat, when we have a simulation, let's say you have a simulation like this. Um, you want to There are different ways that you can export your simulation results. You can export it as a CSV file by just mentioning which variables you want to send uh, uh, to your colleagues, or there is something called simulation executable, right? uh,
Right,
and what we are seeing here is simulation executable. So what happens is, uh, this simulation executable also like creates a .exe file, or the binaries that are
r-
involved in simulating a model, right? So along with the model parameters, it also has those solvers that will help in the integrating the model. So here, when I opened the file, you could see that the simulation result is already there. And then I can check the simulation. I can also simulate it. But there is a
right,
catch here. There is a catch. So when we create a SME, so for instance, when I created this SME, the binaries, they are platform dependent. So one might notice that if you're using a Mac, and this SME I created using Windows, so in my platform I cannot, as of now, create binaries for that is available for Mac. So I will be able to access the results, see all the results, but I will not be able to simulate it, because for integrating I need some code which is platform dependent, right? So when you share
Right.
your models with with someone else, they will be perfectly able to see and plot all the data from your model, but they will not be able to simulate it. So people who are using Mac for now, they can see my results, but they will not be able to simulate it. And my objective for this model is not to simulate it, right?
Right.
But Vedat,
Right.
this looks very boring. We have some data here, but this looks very hard to digest. Is there a better way so that I can consume what is
Yeah,
happening here?
yeah, yeah. We have animation for that. We can just click on it
Oh,
and
right.
see what type of thing happening there.
Okay, let me click so to go to the animation, we have this jumping ball icon here. I clicked on this icon, and we have something mechanical looking. I have no clue what these things are. But before we dive into Vedat, this looks similar to one of the images I showed here.
Right.
Is it the same?
Right. That is the same. It belongs to
So,
the same wind turbine.
so here you are saying that in a wind turbine we have this very big blades.
Right.
Perhaps they're rotating at a speed, and then we have a planetary gear which is something like this, and then we
Right.
have a three gearbox thing.
Yeah, yeah, three
Can you
stage
just
gearbox.
can you just explain me, like, how is this arrangement, like in a real world wind turbine?
Right.
What am
Yeah.
I seeing here?
Right. Here we are looking at a blade where we harvest the wind energy from, and that blade, let's say it rotates really slow RPM. Let's maybe 25 RPM, really slow. But to generate energy, we require higher RPMs. Let's say maybe 2000 RPM. So we need to somehow increase the speed of the shaft, the outgoing shaft, or shaft ingoing the generator.
Okay.
So that is why we need to we use gearbox.
Okay, so we need a
Here,
mechanism to convert the slow speed into a
right,
speed that we can feed to our motor, and that's
right,
why we have this gearbox. But with that, why not just use a single gearbox with a bigger wheel? Why do we need a planetary gearbox gearbox? And what is this planetary gearbox? We have something called
right,
sun, planet, ring. What are all those things?
right. So the gear ratio, the transmission ratio we are trying to achieve here is really huge. It
Okay,
is like 1 to 7 to 7. So assume that you have a one spar gear, which is really small, and just name it, size it, and then you want to just create another, which is a mesh with that. It has a gear mesh in between, and
right.
7 to 7 times larger than that. So
Okay.
it will be it
So
will
it will be
look
half
like
the size of the
really
blade.
ridiculous, right? Right.
Okay. Yeah, so to reduce the dimension, we are having a planetary
Right.
gearbox and a three
Three
box
stage
gearbox.
gearbox. Right.
So what I see is my blade is attached to the sun wheel, which is in the center.
No, actually,
No?
carrier. The carrier you
Oh,
see
okay.
over there. Yeah.
The plate behind it.
Right. Exactly.
Okay. And then that rotates, and because of that, the ring
Yeah, yeah.
something
I mean,
rotates.
yeah, because of the interaction between the ring carrier, those
Hmm.
planet gears we are seeing that they can also rotate around the carrier
Hmm.
on their or yeah around their own axis. And also we have sun wheel in the middle, which is connected to another shaft going to the three-stage gearbox. You show that the one next to it. So that creates, let's say, 1 to 11 gear ratio.
Right,
And then we go on to the next part,
right.
second part, three-stage gearbox, and we keep increasing
Yes.
and increasing
Okay, so
in
basically,
total.
these are the details of how we go from a small RPM and to a higher RPM, and then there are different types of gearboxes used for those purposes. Perhaps those gearbox have uh, some other things as well, like that they can handle high torque. Perhaps they can handle high RPMs. Based on that, there are
Right.
perhaps different type of gearboxes. But for today's session, I think Just
Yeah,
having this
that much
understanding,
of level, yeah.
this
So we,
understanding that so but Veda, this icon looks, this looks boring, and it's a static image. I'm not
right,
impressed. Let's open our result here, the
right,
animation, and then let me just reduce my time scale. Let's say 0.5 second, and then let's simulate and let's see what happens.
right.
Okay, so I could see
Something
that
is happening.
something is happening. I could see my planet gears rotating. Let me slow it down further. The thing is, it took me a long time, so could only manage 4 seconds. But Vedat, why, like, this doesn't look complicated that complicated that it would take such a long time? Why it takes such a long time to simulate?
Yeah, you see each uh, yeah tooth over there in contact.
Hmm.
Whenever contact happens, we trigger an event.
Ah, okay.
So that is why it takes that yeah that much time. So
Okay, so we
right
are
in
actually
whenever event happens, we stop the simulation and try to solve what is the solution at that change location
okay.
of the time, and we continue.
So
So
whenever those two gear teeth are in contact, we're actually computing what is the
right,
force acting on that gear interaction, and
that
that is
gear,
the
right.
arrows that you are trying to that we are seeing here, right?
Yes, yes.
Okay, right. So the objective of this model is to model the contact forces. So if I
Contact
see,
forces and the effect of those contact forces on the gear teeth, let's say.
okay, okay. So we want to understand if those stresses are within the design limit, else it will lead to gear tooth failures, like
Right,
those kind of, or
right,
to understand the
right,
cyclic stresses.
right.
Uh,
And all these component here we see the shafts, so those are all flexible.
okay,
So flexibility related dynamics also taken care of.
right.
Right. And
Vedat,
we have many questions accumulated here. Maybe we can
yes,
just try to answer those.
yes,
So right. One is asking whether the 3D shapes are in the library. Yes.
yes.
Yes, it is. It
Vedat, I
comes with
also
the
noticed
product.
one thing, that without the SMA, I was able to open the animation as well. Perhaps we use the components from the Modelica library, because of which we are able to do it, or am I wrong?
No, this cat shapes looking like thing
Okay.
is the system modeler thing. It belongs to rotating machinery.
Oh, okay, okay.
So
So I
it
need to
comes
have
with this.
SMA to have the animation running. If I don't load the SMA, then I will not be able to see the animation, right?
Right.
Okay.
Right. Right.
Because the SME file that we mentioned only has the results, but the assets like the CAD objects, or some CSV files or other assets, they are present in the SMA. So we need the SMA to see the animation. That's what you're saying.
Right. Right.
Okay.
Yeah. Yeah.
Okay.
And
Uh,
other than that, we have another question. You can answer that, Ankit.
could you
So
repeat
yeah,
how to open the
one.
animation? W- w-
Yeah. Let's show. Yeah, that is the easiest question we get.
Okay, yeah. So I picked the easiest question. So to open the animation, we have this ball, this circular symbol here on the top right here.
Right.
I click on it, and then I can see the animation. And as Vedat pointed out, to view the animation, you need to have the SMA loaded. And with the SMA loaded, I mean you need to have the rotating machinery library loaded, because this file has all the CAD objects that are needed to create the animation. So with the
Right.
SMEs, we can see all the curves, but to see the CAD objects, we need to load the SMA. Right? Okay, Vedat.
Right.
Yes.
Other than that, one is asking what is the difference between SME and the FMU?
Um, okay.
Or
Well,
can we open FMU? Right. What
so
is the difference? Yeah,
so
FMU and SMU.
yes.
That was the question.
So okay. Uh, uh, So when we talk with SME, so SME is a file for system modeler, right? So anyone who has system modeler, they can open the result file. So you need a system modeler installation in place. to see the results. So it is used to share files between system modeler copies or system modeler installations. And FMU is a standard. So people who are, uh, um, let me open up. So Vedant, if you can, in the same time, can explain what is FMI.
Right. FM is functional mockup interface or user. So it is a platform where you can export your model, let's say in System Model or maybe another program, let's say ANSYS or I don't know whether Abacus have. So you might create your model in that one and export as FMU. If any other tool which is compatible with this FME tool, then you can just import your model to that platform and use the dynamics in it. So that is what basically FMU does.
Right.
So
So
between the tools, it creates some accessibility.
yes. So I've shared the link in the in response to, in the chat as well in response to the question. So as Vedat rightly said, let's say you have a model that you want to share with another simulation tool, uh, which so with so how can you share, let's say, with a different tool? How can you share a model that you created in System Modeler with a different simulation tool? Like we have a different language, they have a different language. How can we talk to each other? And in order to talk between different simulation products, there is a standard, right? So we compile our model into this FMI standard, and we create different type of objects that can be shared among the different products or different simulation tool. So this is so using this standard, you can share between different simulation tools, including other system modeler tools as well, and that is called and that is the use of this FMI standard. I- Uh, I think let's stick. Let's so far
Right.
what we've discussed. I think this it's good enough. If someone wants to know more about the FMU and how to share it with other tools, we have a dedicated page on where we explain what is FMU, why one should use FMU, and they can have a look at it. But it's also of a way of exchanging your models with other tools, right? Okay, Vedat, let's get back to our model. So we saw in the animation, we saw the results as an animation here, and we saw that this is a high fidelity model
Right.
where you are modeling the contacts between the different teeth, and we are using it to understand the failure scenarios, right? And
Exactly.
I think uh, that's what we can say up to this model, right?
Right. Right. And I guess that much detail would be enough. So if you are looking for like a designing gearbox and to understand why sometimes certain type of failures happening, or you might try to some scenarios whether it is applicable for this gearbox, then this is the right tool to test your conceptual design quickly. You don't need to do back and forth and get the boundary conditions from another engineer to implement your, let's say, gearbox design structural mechanically, like structural finite element model. So this is way faster to test out those scenarios
Right.
and right tool.
Uh,
And
yes.
also we got some question from Francisco. Yeah, Francisco, I guess we said something wrong there. You could see the animated image. Yes, you can see the animated image because the image, the cat thing generated here, it comes with the system modeler. If
Okay.
you didn't have that system modeler, I mean, in the so we have some certain image in Modelica, and
Oh,
this
okay. So Vedat, you want to say is this CAD image that we are using here comes with a system modeler installation.
yes, yes, it comes
Okay.
with the system modeler installation.
So one can view
Right.
it. One
But
can view.
if we had another cat shape which is used in this model
Mhm.
and we don't upload that model SME, then we couldn't open it.
Okay. So you want to say that, let's say I create my own library and my components have a custom CAD shape like that I want to have in my library, and if and anyone else who just wants to distribute the SME, they will not have the CAD object. They would need the model file as well, right?
Right.
Okay, I
Right.
think that should be clear for now. Right. So Vedant, there are so many interesting things here. Like I could so once we share the SME, as you could see, one has access to all the different variables present in the model, and that's why the size of it of the model of the SME is around 300 MB.
Right.
Um,
Right.
right.
One small thing here, I mean, while designing such thing, we are not the domain restricted. Like for instance, while designing a controller,
Mhm.
I mean, we can look at both. For instance, if someone tries to use a controller in a finite element software, I mean, which is not practically available. There might be some tool out there which I am not aware of, but
Right.
it is unheard of. So what System Modeler does, you can do all those things, all multi-domain stuff in one place. For instance, here we have power source, Ankit.
Right.
If you click on that, it has like a controller embedded in. So
Right.
you can just set which
Right.
rotating speed you are aiming. You
Right.
can just set it and get it. So
Right. 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 Just to keep. So what you're trying to say with that the advantage of modeling this high detail model in system model as of now is that you can integrate your high fidelity model like this detailed model with a generator or with your own control logic, which
right.
if you just use a finite element tool, it you will not be able to integrate with something
Right,
outside the boundaries.
right.
We
You need
can
to get your boundary conditions back and forth until you get satisfied with the results,
okay,
until they converge each other at the some level.
right. Okay, and just to
And
mention, we have so people who are interested or who are involved in bearing modeling or wind turbine modeling, we have pre-made
blog,
components that they
yep.
can just parameterize and then they can use it for this rotating machine library, right?
Right, related to this wind turbine blog as well, we have, yeah, model, we wrote a blog about it. You can just read. Ankit, have we shared link or should I? sh-
Uh, right. Um, yeah, perhaps Sergio can help us in sharing the
Yeah,
link for the blog.
I will send it.
Okay. So if before we conclude or before we move on to the other models,
Oh,
if someone really wants to know more about uh, this model, Vedat has written a blog on it, and we'll be sharing the link of the blog so someone can go and read more about it. Right?
right,
Okay, Vedat. Right. Okay. So I think we have taken sufficient questions. We have covered one type of model that one could do, and we have shown that you can also have animations in your models. Um, right. Okay. So this up to this part, it's all right. Let's move on with that to something that we have learned so far, so we don't uh, we don't we don't confuse our audience a lot.
right, right. I mean,
Let's
this was a showcase of sky's the limit phrase, right? I mean, so
yes.
we have so many things we can do with this
Yes,
tool.
and that's and that's the concept behind use different models, right? And there
Right,
are and one thing that we wanted to show is when you create a model, you different teams work on a model. One team is working on a very high detail model, one team is working on a business level model, and one team is working where we integrate with the grid and other types of models, right? So different
right.
teams have different requirements, and one modeler is of course not expected to know all the things, but this is one type of model that is used in the industry, right? Okay, with that, let's get back to our presentation.
Yeah,
uh, right uh, right. So yes, we have seen up to this point, we have covered what is an SME, um, and we have seen the animations. Now let's open our modeling principles uh, file.
right,
Okay, so to open that, you might notice that I have a modeling principles version 2, which I have updated uh, with the model that I will be showing today. So people who want to see the model that I will be showing now, they can download this modeling principles version 2 from the downloads material section, right? Okay, so let's open the different models section, and in the solution, I guess I have the first model here. So with that, we have two models here. What do we see here actually
Right. So
in the presenter mode?
the model above, we have roughly the same skeleton of the model we use beforehand, right? The DC motor and the electrical.
No, but with that, let's before we go into the details, what is the model about? Like, what is the purpose of this model? What are we trying to do here? In the previous case, we were trying to understand failure scenarios by looking at the details inside the gearbox, right?
Right, right,
And in this case, like, what is the objective? Like, we have one model here and we have another model here. What
right.
are we trying to show here?
So here we are just showing that there are certain dynamics, essential dynamics we want to look at, not all of the details related to contact force, etc. Those dynamics we're interested in, how much power we can generate if we have certain power implementation in this simplified wind turbine gearbox.
Right. So what you're trying to say is,
Wind turbine, sorry.
yes. So what you're trying to say is, in the first case, we focused on the gearbox, internals of the gearbox, and in this model, we are trying to understand the big picture. Like, if we focus on the models that we have done so far using the business simulation library, we have we are using this model to understand how much energy we can generate from a wind turbine, right? So the objective here is, given a location, given a wind speed, how much of the energy I can retrieve, right? How much of the energy I
Right,
can retrieve from particular location, given the wind speed and all those things, right? And then in the bottom, so these are basically both kind of the similar models, but with different ways of presenting the same results. One you
right,
could see is the system level way of doing things, where we are just interested in the energy scenario, like how much is the available energy and how does the energy loss happens, and at the end how much energy is left in our energy storage. Whereas if I want to understand how the torque and the rotational speed they are changing, and I am interested on the engineering side of things, then we have the very same model but using the different engineering principles, like looking into the rotational energy and looking into the electrical form of energy,
right.
right?
I mean, the model below is for the, let's say, for the non-engineers, maybe.
Mhm.
So, I mean, you might assume that you have that kind of system. It has its own dynamics. But as Ankit rightly said, we are just looking at the like a conceptual or the philosophical level. We are saying that we have some power source, and that power source, which is the wind over there, and can be treated as like a maybe money source, maybe some income source for the business simulation level over there at the way at the bottom we are looking at.
Right.
So we are just making them look alike to understand the modeling concept
Or
to simplify.
to see how they're analogous to each other,
Right,
right?
right,
And let's get started. Let's start. So in today's session, we will be looking into the engineering side of things. We will be trying to model the gearbox. But we before we go into the hands-on side of things, let's try to uh, familiarize people with what we are trying to do, so people from non-engineering domain can have some understanding of what we are trying to model in today's session, right?
right,
So with that, if I start explaining, and correct me if I'm wrong somewhere. So here we have a wind source which looks like a ramp, and then what we are doing here is we are converting the wind speed into some kind of energy, and here that energy we are trying to pass on to our uh, growth source, right? And then
right,
we are creating an available energy, and this if I think in terms of my wind turbine, that would correspond to the energy stored in the wind blades, right? When they're
Right.
rotating.
Right. It has an inertia over time when it gets speeded up. So it will store some energy in it. Even if we cut the wind, it might still continue to rotate until all the energy drained out. So
Right.
that is the similarity we are trying to put forward.
Right. And then we have a gearbox, which changes the RPM of things, but what happens is the energy is conserved, right? So energy
Right.
is the
Right.
same. It's just the energy is being transmitted from the blades to the gearbox with a given rate, and that rate perhaps is determined by the gearbox, right?
Right.
And also one might think that uh, when there is a contact inside the gears, there is friction involved, and there is perhaps some losses inside the gearbox. And that loss we are modeling with the operational loss, and with the gearbox loss component, there is some energy loss there.
Right, right. We can consider this, Ankit. I am not an expert in that domain, but like
We
the like gearbox, we can consider that as like a leverage. I mean, for a certain amount of time, we can just multiply our stock share and penalize us accordingly. And for the gearbox loss, it might be maybe considered as, let's say, the inflation, maybe interest rate, or maybe some maintenance costs, which we are paying continuously.
right, right. And then without here, if once after the gearbox, we have the energy that is available on the rotor side of the motor. So it's at the input side of the motor, and that we are representing with this stock, which is this after
Mhm.
gearbox stock that we have here. And then one could imagine from this input we convert the energy and store it in energy storage, and we have this a proportional converter which converts the available energy into energy storage. And then when we do that, perhaps we have some AC to DC conversions, we have some other electrical circuitry, we have coil resistances and different types of losses, and those losses we store in the electrical loss stock, right? So in
Right,
using this model, one could actually uh, tune those parameters and try to look at the big picture from the energy level, and not go details into how the RPM is changing, how the torques are changing, how the current is changing, but just to look from the top level, like how things are operating, right?
right,
And perhaps one can use the output from different stages, and they can compute some financials as well, like for per kilowatt or for per joule of energy that is produced, how much money you can generate, or how much for per joule of energy that is gone into the gearbox loss, how much monetary loss is happening. And those kind of analysis can be done by extending the business simulation way of modeling those things, right?
right,
Okay, Vedat. So I think uh, with this we have given a small introduction of two different types of ways of modeling, using the system dynamics way and using the engineering way of things, right?
right, right.
Let's get back and begin our modeling journey for today with with the engineering side of things, right? And we
Yep,
will try to explain the different components, so that people who are not uh, used to this kind of components, they can understand what we are trying to do, right?
yep,
Okay, so let me get back to my uh, modeling interface. I will open exercises section. Right. So in order before I have a clean model, and it will take me a lot of time to create all the models. One thing that we could do is we could reuse the models that we had developed in our interactions, like don't neglect interactions course. So I will use the model that we have developed there. I will go to interactions, solution, and I will go to step 5. And let's copy this model here from the interactions, solution, step 5. And then we will try to build upon this model in today's session, right? Let me copy it here, Control C, and use different models, Control V. Right. Okay, with that. So we have the basic components in place. Uh, right. I will just arrange it properly. Okay. Right. So yes. So what are we missing here with that? Wind. We have a wind source represented by a
Right,
ram, and then
right.
what we are trying to do here is we are converting the wind power to torque, right? Uh,
Exactly, exactly. So what we are missing here, I would say a gearbox. We need to somehow.
yes,
Oh, but before that, you are maybe missing blades.
yes, right. So if I look back to a model, let me close it here. So this is what we are going to model today, and this is flipped.
Right.
So one has to note this. Uh, so here we have the wind speed, and then from this wind speed we calculate the torque. How can we calculate the torque from the wind speed with that? Is there a way to do that?
Right, there is a way to do that. You mean a
Like
torque equivalent from
yes,
wind speed to
torque.
torque?
Yes,
Yeah, yeah, there is a like a area where you can, if you know the dimensions, then
right,
there is a direct conversion from wind speed to equivalent forces. Of
right.
course, this is like some kind of simplifications, but it will be enough in our case.
Right. So let's assume that with this wind we have those things already calculated, because there are formulas which help us in calculating those torques from the wind speed, right? And let's say we have the torque, then we have this inertia component that represents the blade, right? And after
Right.
that we have a gearbox, and this gearbox mimics what we saw in the detailed model, right? We have a planetary gearbox, we have a ideal gearbox, and uh, to
We
uh,
have a
eh,
shaft in between.
we have a shaft in between which mimics the inertia, right? So for people who are not from the mechanical domain, Vedat, uh, what do we mean by this torques and the shafts and inertias? What is inertia like? It's basically, perhaps I would say, when you have a shaft, it's the ability to keep rotating even if you don't apply any force, right? It's this momentum, it represents this
Right,
momentum kind
right.
of.
Moment is the right term. So we can load an energy to that
Mhm.
when we apply the torque. It starts rotates, and we know how magnificently it rotates. That is the term of the momentum for a rotating blade. So then that thing is in a way stored.
Mhm.
So as long as we don't spend on that thing, we don't attach that thing to another thing, and there is no resistance, it will keep rotating and it will keep increasing.
Right.
Uh,
So we have this mechanical torque, which is kind of a force which is trying to rotate the blades, right? So when we say torque, we are trying to have some kind of a analogous to a force. If we think of a mass, like if you think of a linear system, um,
right,
right? Okay. So then we have a blade with an inertia. Then we have the ideal planetary gear, and this is what we saw in our previous detailed model. Then we have a shaft, because this uh, ideal planetary and ideal gearbox, they don't have an inertia on their own, right? So these components do not have an inertia. So we have a internal shaft inertia to represent
right,
their momentum, right?
right. We in a way we lumped all gearbox
Mhm.
to do that internal shaft component in terms of inertia part.
Okay, right. And then once we have the gearbox, similar to the blades, we come to the rotor side of the motor, and then we represent that inertia as with this the same element, right?
Right,
And then, as you mentioned, in this system there are losses, there are friction losses at the bearings and other losses which are modeled by this damper component, right? So this, and with this damper we are thinking about the rotational friction, right?
Exactly.
Okay. And then we have the model that we have already modeled before, EMF component that converts your rotational energy to electrical energy. So that components helps in those conversion. Then we have the inductance in the in the coils, which basically stores the magnetic field, right? And then we have the coil resistance, and we have a battery which we are representing by uh, a voltage source. So we are assuming that we are not interested in the battery dynamics now. So we are just assuming that we have a 12 volt, uh, a battery with 12 volt voltage difference across its terminals. Right.
Right.
Okay. Um, is there any question up to this point? Or
Ankit, we have new components up there. I mean, you connect that and it says some kind of sensor. What what are those components you
oh
connect?
yeah, yes. Uh, right. Right. Okay. So with that, let's start our modeling process. Let's start
Okay,
with
okay,
modeling up to this. Then we will find out why there is a need for that. Because
I see,
currently there is
I
a
see.
no need. Let's try to start the modeling process because that's the fun part,
Right, you are
right?
right. So,
So
okay, before going forward, I want to summarize why we are doing this, Ankit, now.
mhm.
So, why this is important. I mean,
Yes,
we start with huge, really high fidelity wind turbine model, and
mhm.
we come to that. And
Yes.
why didn't we use that model to model this, for instance? Why
As you
did we
said,
continue?
yes. So Vedat, when we are uh, as you said, for this high fidelity model, it took you 2 hours to simulate, right? And imagine if you want to test different planetary gear ratios, different three-stage gear ratios, it would take a lot of time for you to simulate those scenarios, right? So we need
Right.
to start simple with only the essential dynamics first, and then we want to
When you
see.
say, yeah, you said essential dynamics. Why those dynamics are not essential? What make us think, okay, those dynamics are not essential?
Oh, sorry, maybe I didn't. Those are not essentials for our modeling purpose, where we are trying to just understand how the flow of energy happens. But for
Right.
instance, if someone is interested in the gearbox failure analysis, then for him those are the essential dynamics, right?
I see. Yeah.
So in our case, we are just considering, like, if we have this rotor system, if we integrate to the electrical system, what are the changes that we could see, right? And we are trying, so we use this simple model to get a first hand understanding of the different transmission ratios, different effects, and then we can go into more detailed model later on, right? So we need to
Right.
start simple first and without
Yeah.
neglecting interactions.
Yeah.
Okay, so we will need a shaft, ideal planetary gearbox, an ideal gearbox, and so on, right? Let me open my model, and to find this rotational components, we will use the Modelica library. And inside Modelica library, we have the mechanics library. And inside this, we have the rotational library here. So as we are modeling the rotational dynamics now, we will use the rotational library. And let's use the components from that. So if I go to the components, we have the inertia, which we can use here for the blades. Let me rename it by pressing F2 and giving it the name blades, right? Once we have the blade, we would use the ideal planetary gearbox. And Vedad, as you mentioned, uh, the bigger side here,
Right.
which is the plate, right? That is
Right.
attached to the blades, right?
Right.
So I will keep the name ideal planetary as it is. Then use the ideal gear here, and we will also use the inertia component to represent, as I said, the inertia of the gearbox system as a
Right.
whole, right? So I will just rename my inertia to gearbox inertia. click OK. Right. And then let me connect my shaft to the ideal gear to the gearbox inertia to the ideal planetary, and ideal planetary to the blades, and blades to the torque. Right.
Wow, it took you 10 seconds to model a gearbox, Ankit.
Now I'm not completed yet.
Yeah.
Let me see our model if I'm missing anything. Okay, so now we've connected the ideal gear to the rotor, right? Where there's one more thing that is missing. Let me flip this horizontally. We have a connector over here with that, uh, which needs to be connected somewhere.
Right.
Like why would we need this connector to connect it to the fixed thing? Um,
Right. I guess that one is the ring. Is that the ring?
kind of.
Okay. I noticed that I haven't used this component beforehand,
Yes,
even if, yeah, I
yes. Let me.
happen to design the largest one.
Yes, uh,
Okay,
yes.
carrier.
This is
Is that
the
the carrier?
this is the carrier,
Yeah.
right? So the thing is, we want to
So we
fix
have a
we,
ring
we
which
want
is
to
fixed.
yes, we have a
Uh,
ring which is fixed, and the other things are rotating with respect to it, so we need a
Right.
reference, and that reference
Right.
could also move, but in this case we want to fix it. That's why we have connected the reference to the fixed thing, and then all the other computations are based on that.
Which is a housing. That one with a ring which
Yeah,
should be connected as housing.
which should be called a housing.
Mhm.
You're right. Okay, so now we have, let me rename my ramp to wind. Okay, so now we have our wind, we have the torque that is created by the wind, and that torque makes the blade to rotate. Then we have the ideal planetary gearbox, the gearbox inertia, uh, then we have the ideal gear, and then we would have the rotor. So I will rename my shaft to rotor. Right. And then we have the friction element to represent the friction. uh, it's a lumped friction. I would have made
Right.
several different frictions at different stages, but for now let's take one friction element and attach it to our system, right?
And we had inertia, which
um,
okay.
yes,
Param- yeah.
if I get, let me close this. If I get back here, I think we have the model as it is. The
Right.
only thing I want to change now is, rather than, okay, it's
It
just
is
for
good.
it's
It
just
is just it is
yeah,
simplified better. Yeah.
it's just for demonstration. So let's keep the capacitor in place.
Right.
Let's see how we break our models.
Right.
but, but anyways, let's okay. So with that, once we have a basic uh, components in place, we thought about our system, we discussed the different components, we have all the components here. Let's try to give it some values, right? A small
Right.
s- like a simplified values, because then we have to do a lot of computation for to getting the parameters for a real
Right.
wind
Right.
turbine. So let's take some kind of values here. So let's say we have a wind speed of wind, the torque
Yeah.
created by
Fine.
wind as 5 newton meters
Right.
here, and then let's say a blade of 10 kg per
Oh,
meter.
maybe even smaller. Maybe.
Yeah, yeah,
It,
because the actual blade will have 10 to the
right.
power 10 in to the power
Right.
5 kg meter square, but let's keep it simple at 1. Let's see if things
Yeah.
don't break first, and then we can fix or update the parameters as we go. And then for ideal gearbox, with that we have 100 by 50. Like how do you calculate this transmission
So
ratio?
it says that we have input of
Ring teeth.
let's
So perhaps we have a ring teeth of 120 ring teeths.
right, and the sound it has only
20.
50 of them. Yeah.
So let's say we have a planetary gearbox
Right,
where the
acceptable.
outside has 120. So the outer gear of the planetary gearbox, the number of teeth it has, and let's say it has 120, and the smaller, uh, the sun teeth, the smaller one, let's say it has 20, right? So
Right.
we use those numbers here,
But
and
this
then
is a
for
simplification. In reality, you need to take into account even planetary gear. So this is just simplification. Keep
yes,
in mind that.
yes, and for the three stage or four stage ideal gear, let's take a transmission ratio of 17,
Right, this
or
is the total ratio
right.
from between input and output.
For the ideal gear, you mean? For the three stage
Yeah,
gearbox?
for the three-stage gearbox. I mean, in our
Right,
case, we had the three-stage, and in each we had different. But when we multiply all of them, we get
right.
one to, let's say, 11.
Right. So let's say the resultant is 17 for
Right.
our gearbox.
Yeah.
Okay, but these values are just for our modeling sake. Uh, so now we have a system in place. Let's set the experiment setup for 20 seconds and let's simulate the model. But before we simulate, Vedat, is there any question that we should?
Yeah, we have one question. Okay, is there a Mac compiled version of the Windows turbine gearbox model for the
Uh,
SME?
yeah, it depends on me. So I didn't
Mm,
have Mac when I was simulating this model. I had Windows with me, so that's why Randy would not be able to simulate the model, but he should be able to see the result and plot the animations.
Right,
That should be
but Randy,
possible.
what you can do, you can download the library, and over there we have wind turbine gearbox model, which is exactly the same model Ankit used, so you can just run that model.
Yes, but it will take a lot of time.
Yeah, it will take a lot of time, but you will have so many information about your
Yes.
gearbox.
Yeah, and
Uh,
with that, I just took a random capacitance values of 10,000 farads. I don't know what is the expected capacitor value. I just used it for storage purpose.
right,
And let's simulate our model. Let's see if we break something or not. Oh,
right.
Randy says he ran the library and he has a simulation now. That's great.
Yeah,
Okay,
and yeah, Nicholas, I will answer your questions at the yeah at the end of the presentation.
right.
It requires a bit time, so
Yeah. So Vedat, we were lucky. There was no error so far.
yeah. Oh,
Okay. So um, let's look at our model. Let's say for the blades, let's try to plot the rotational speed of our.
yes, John, it was 5 as far as I
Yes,
remember the torque parameter.
yes. uh, and we will be changing everything right now once we
Right,
see the
right,
results. So with that, for the blades, we want to plot the rotational speed of the blades, right? We want to see how fast those blades are rotating. Let's
right,
try to plot it. So in order to plot it, we will go to the blades component here, and then we have the W, the rotational, um,
right,
uh,
angular speed.
the angular speed here, right? And that is in radian per second. So I opened the blades component and I selected W, which is the angular velocity. And I like to see the results in RPM because I'm used to RPMs rather than radian per second. So let me change the display unit. I do by right clicking on the y-axis and selecting RPM. So you see that we have very small RPM with that. Like this is like I'm
Right,
not even sure how slowly it is rotating.
right,
Let's try to change our our wind parameter, right? From 5 Newton meter, let's say 50 Newton meter for now.
oh,
Yes,
still so less.
it's also maybe
So this is
5,000 Newton meter
right.
would be right here. And here we have a slow a blade rotation at 6 RPM. But as
Let's
you
set
said,
110. Yeah.
right? But because as you said, the for big you
Yeah,
would
the
expect the
larger
RPM
it
of
is,
around.
yeah, the slower it gets. It is
Yes.
like 20 to 25 RPM for the largest
So let's say
wind turbines.
so let's say let's use 10,000 Newton meter for now. Yeah. So around 10 or 12 RPM, right? Um, right.
Right?
Okay. And we see this dynamics here. Okay, okay, fine. Uh, Let me do a subplot and plot my wind values here. So I go to the wind and I plot my y. So this is the input from the wind. So there is initially there is no wind, and then uh, the torque from the wind is 10,000 newton meters for now, and then it is remaining constant. And you could see this is the dynamics that we are seeing. Okay, with that, now we have seen the blades. Now let's see what happens at the outlet of our ideal planetary gearbox,
Right,
right?
right.
Okay, so to do that, let's go to the ideal planetary and let's try to plot it.
Sun, right.
But
Uh,
Veda, there is no way I can plot the speed outside here. I don't have a parameter or I don't have a variable that helps me plot it. How can I plot the speed after that?
right. Yeah, it's a good question. So that that was the reason why Ankit put those sensors to just
Right.
measure what is happening there, because
Yes.
some components might not have the variable we are looking at. To compute those, we need to add sensors.
Yes. So, as you rightly said, we need to compute. Like in this case, we didn't have the variable accessible to us, so we can go into our sensors package and we can see if there are any relevant components that we can make use of, right?
Right,
And inside our rotational package, we have the sensors sub package, and here we could see I can plot the speed sensor, I can plot the angular rotation using angle sensor, and several other sensors, right?
right,
Let's use the speed sensor for this case, right? So let me drag it in here and let me flip it, or let me rotate it instead, and then uh, I will connect to the outer end or to the left end
uh,
of the
right,
planetary gearbox, and
right.
let me
To
rename it
sun,
to planetary output, or
or maybe sun
okay, sun wheel speed,
will,
right?
right,
Okay. Uh, so while we are at it, Vedat, let's add other sensors as well, so we don't have to redo it again. So
right,
let's duplicate this. So I will do select it and I will do Control D, and then let us calculate what is the outlet, what is the speed after the ideal gearbox, right?
right,
And then let me connect, use the connection line tool and connect to the ideal gear, and let's rename it to ideal gear speed. And with all the speed, I'm referring to the speed at the outlet, or at the uh, or towards the uh,
generator.
yeah, towards the generator. You're right. Okay, so once we have this, let's go ahead and simulate it again. Right. Yes, and once we have the simulation done, let's go ahead and um, let's plot the sun wheel speed. Let me select my top subplot and then select the sun wheel speed, and then I could see that the direction of rotation for my sun wheel speed is in the opposite direction to the direction in which we had the initial blades rotating.
Does it make sense? To me, not.
Uh, I don't know. That's what we are getting out of this model.
Yeah, can we look at the model? Maybe we might flip one of the components
So here we
to
have the ideal planetary gear, and we have defined the number of ring teeth to sun teeth to 100 by 50. Uh, Things looks fine so far to me.
Oh, okay. Maybe we need to connect. I guess what is happening while we are reading that sensor and
Hmm.
from the accessible variable,
Hmm.
I guess the sign flips.
Oh, okay. Maybe,
Yeah,
maybe.
because we haven't compared Sunwheel and Ideal Gear yet.
I
which
have right. I've connected it to the ideal planetary gearbox.
right? Can we look at the simulation results again, Ankit?
Yes. Okay.
So
Uh,
yeah, that is the blades, and we could access it, right?
yes.
It is
For the
not from the sensor, right?
yes, the blades is not from the sensors. It is from
Right,
the rotational speed here. Should we use it from the sensor as well?
right,
Okay. Let's do it. Let's duplicate it. And so I did Control D, and let me connect uh, to this end of the planetary gearbox. And this is the carrier you said, right? The
right. That's the carrier.
carrier speed. Okay. Yeah, that's a good way of, rather than going through the
Mhm.
internals, let's use the speed at the start and let's simulate it again. I saw there was some question regarding this model, Vedat, or was there not?
Related to this one,
Or maybe uh,
no,
maybe
yeah, no,
Sergio
it
has
is.
already answered it. Who knows? Okay, so once we have the model simulated, let's plot the carrier speed, and let me plot it here. Right, I get the same Vedat as the angular speed here.
Right. Okay.
Right, right. So
Hmm.
perhaps what we should be interested in only uh,
Amplitude of it.
the amplitude of it. Right,
Right.
right. But okay, fine. For now, let's use what we have, and let's say that we have the rotation in a different in the opposite direction, and we have the output speed at 71 rpm.
Right.
Right. Okay. Fine. So after the sun wheel, we have, if I go back to my model, we have the ideal gear speed after the ideal gear 1. So let's plot it. I'll go to the ideal gear speed and I will plot the ideal gear speed here, which is the green one, right? Okay. Um, I kind of want to plot all of them together with that. So what I will do is I will use an absolute uh, value instead, so that it is easy
Right.
for me to visualize. So what I will do is once I have the output, I will take an absolute of this value so that I can see all the three things in the same with the same sign, right? And to find the absolute value, I will go to my blocks and I can find it under maths, and then we have the absolute value here, right? And let me rotate it and connect to the ideal gear speed.
Sorry, Ankit, can you just a question that came up? Can you show which sensor are you using for?
Hmm. Right. Okay. So for rotational, uh, for the rotational
Which library
speed,
this
the
one?
speed sensor. So for the speed sensors, I'm using the sensors package inside the rotational
Yeah.
library.
Okay. Where can we find this rotational as well? It is not the
Okay,
rotating
okay,
machinery,
okay,
right?
okay. No, no, no. So yes, so inside the Modelica library, if you open the Modelica library, we have the mechanics package inside, and inside the mechanics package, we have multi-body, rotational, and translational. In this case, we are um, using the we are in the rotational domain, so I use the
Right.
rotational sub package, and then we have a sensor sub package inside it, right?
Right. Yeah. Thank you.
And then what I want to do now is, since I have a different direction of speed, I want to visualize it properly. So I'm taking an absolute of my sensor values, right? So I can plot all of them together, uh, right? And then let me duplicate it again and then plot the values here as well. So absolute 1 and absolute 2. I should have renamed it, but yeah, let's plot it first. Right, and let me clear my plot again. Uh, so we have speed from the absolute. Okay, this is nice. And then absolutely, it's just that whatever makes my visualization of the results better, I really appreciate those things. And then we have the what were the blades, right? Um,
Right.
yeah, the blades RPM, right? And if I try to plot the measurements when we have reached stability, you could see that my for that configuration that we had, our inlet um, or the RPM of the blades was around 12 RPM, and the RPM that we are getting at the rotor of our generator is around 1200 RPM, right? So here
Right.
we could see that uh, with your high fidelity models, what are the transmission ratios that you used, and then
1 to
we
7 to 7.
yes, and those transmission ratios we use in our ideal components, and we could see those conversions, right? So rather than creating those big models, we have a simplified version, and we could see how the RPMs change over the different range. Okay, uh, once we have done this, Veda, it would be nice to see the electrical response. We have not done any change. We have a capacitor
Right.
in it. It would be interesting to see how the current characteristics change, right? So let's check it by plotting the values inside the resistor. So we have the resistor component here, and let's plot the current inside this. Right, and as you could see, the current is skyrocketing. We have a current value of 90 amperes. S- for it sounds very large for our toy model actually.
Right.
Yeah. And then let's plot the voltage across our storage. And as you can see, as um,
Voltage is increasing over
voltage is
time.
increasing over time,
Can we see whether it just reached
let's
the steady state?
yes, let's increase our stop time and let's see if we can reach steady state. It seems to be going on increasing. Uh,
Right.
right. Is it related to my capacitance that we have? What happens if I have very small capacity? Right. Then I could see that it has reached like it has
Steady
reached
state.
saturation after a while, right? So I could not charge even if I produce a lot of energy. I could not charge it further, and then let's
Right.
let's increase it by 10 Faraday, right? So here, and I will increase it further, change the time to hours, 60 hours, and here you could see. So Veda, from here we could see that after around 15 hours, our storage capacity has saturated. We are just storing the charge, and we and after
Harvested
a certain
by
time,
this wind turbine.
yeah, and after a certain time we are just losing all the energy, right?
Right.
So we are not using it further, and this type of dynamics we cannot plot using our business simulation components, right? So in our, if I go ahead and compare the two models, uh, let's
Right.
let's open the business simulation library.
Maybe we could.
Right, we could of course, we
Yeah.
need to add more
Hmm.
more dynamics inside it. Perhaps this and energy storage container has a limit inside it.
Right.
So when it reaches the limit, uh, we we stop the things, right? But as you get to see, the business simulation library, if we had used only the business simulation library, it has its advantages. Like, we can quickly get an idea of what are the energy loss components, and what are the different sources, and how the system can be divided into different components,
Right.
right?
What type of energy flow we will have,
Yes.
and that thing actually, in a way, like the core philosophy of this whole Modelica modeling, like a causal modeling. We have an energy source at one end, and we might have a sink and we create some energy difference. And because of that energy difference, we see energy moving from one side to another.
Right.
So it is quite similar to bond graphs. I saw that
So that
system. Have an eye.
there is some audio.
Yes, I also hear that.
Is it Sergio? Okay, that's fine.
No,
Right. So to summarize, Vedat, uh, when we had this system dynamics model, we could quickly see the different energy sources, as you rightly said, where is the energy being lost. It quickly gave us a quick picture, right? But
right,
if we want to really go into the details of the model, right, like how a wind turbine actually works, like we see the turbine rotate very slowly, 15-20 rpm, but we could see that by using the gearbox and for our generator, the speed actually increases so much, like from 20 rpm to 1200 rpm, and it rotates so fast, right? And then how uh, the conversion is constrained by the storage capacity. If you reach the storage capacity, you cannot store the energy any further. You have to sell it to the grid or consume it, right? Or you need to
right,
have alternate battery arrangements to store those things. So it tells us about the constraints of our operational um, components, right? So just to summarize, what we have seen so far today is three different ways of modeling. One is a high fidelity model to model the failures inside a gearbox with detailed stresses. Then we saw a big picture model to get an understanding of the energy flows. Then at the end, we created a simple model to understand how the RPM changes and how the current in the circuit is changing, and how we are coupling the rotational domain and the electrical domain. Right. So you could see that with different models, we could try to answer different questions regarding a wind turbine, right? And it depends on our modeling objective uh, of to choose which type of model suits it, right?
right, right.
Yes.
And yeah, we have some question. Maybe we can
Yes.
start to answer. Let's start with
It is after a long
Salome
time that I felt that actually I could cover what I thought I should cover,
in
and
time, right?
I could not say I could cover everything. So there is a homework for the electrical engineers out there. Uh, like we saw in our case, in our model, uh, we we used the speed sensor. We took an absolute value of it, but in our model there is no brake with that, or there is no clutch. So if the speed
Right,
of the wind exceeds something, then we have no way to manage those scenarios. Like what if the wind speed exceeds the threshold, right? How can we
right,
stop? How can we have brakes and clutches in our model, right? And for people who want to go deeper into this engineering model, they can have a look into the step 2 model. And then this is also a very simplistic model, but it gives you an idea of how do you create controllers, right? So given a sensor output, how what are the logics that you can work on, and based on that logic you can engage or disengage a clutch, so that you can add those safety aspects to your model, right?
right,
And this is also one of the advantage, that when you use this simplified electrical model, you can create your control algorithms. You can test your control algorithms quickly, right?
right. Yeah, that's also another superiority of system model, the Modelica line, where you can have all this type of data type, like you have real inputs other than integers and booleans, all type of inputs
Right.
you can have in your model.
Right. When you mention that, Vedat, there is something I have not mentioned to the audience before, and some people might get
Hmm.
confused. So here, what we have done is we have a real output from the sensor, and we have a reference, and we have a simple on-off controller, right? It it uh, it checks if my speed is within the allowable range. It checks it, and it gives me a purple signal, and this purple signal is basically the Boolean signal. So it tells either be on or either be off. And then
It
we
is
have a
like a
switch
flag. It
mechanism
says, okay,
like a
now
flag.
time to go or time to stop.
Yes. And then based on this flag, we have a switch which switches between two different inputs. If the speed goes beyond a threshold, then disengage. If the speed is within the threshold, then engage. Right? So those kind of logic one can think of and expand their models using these real outputs and all. Right?
Right.
But I think this is more for the people from the electrical engineering domain or people who are in the control systems domain. Uh, so they can have a look at this and they can expand their models using it. Yes. So with
Right.
that, let's take some questions.
Yeah, yeah. And so I'm asking whether we need to flip the model horizontally. No,
Uh,
so me, yeah, Ankit, go ahead. So
uh,
the model we had,
mhm.
the one we developed, and you said it's just like a flipped. So do
Yes.
we need to flip it back so that we get the exactly the
No.
same model?
Uh, uh, the advantage with this model with that, it will help us to think more.
Right,
So now everything is flipped. uh, you don't need to flip anything. One thing I think one should keep note or one should think of um, is the direction of the ideal planetary gearbox.
right, right. That might cause some changes.
Yes, and I think with that this is wrong here,
The Yeah, that's why we got the different results.
or
It's the
that
other
was a
one.
different model. uh,
Yeah, that was the other one, right? This is the original one.
yes, yes. So the
The
outer one.
direction, yeah, the direction might cause changes.
Yes. So when you are flipping this, I think it's an exercise for people to try out both ways and try to see if how it has an impact. I think that can be an exercise. So when you're trying to flip the components, the planetary gearbox is the only component which I think uh, the planetary gearbox and the ideal gearbox. One has to be
Ideal gearbox,
careful.
yeah.
One has to be careful, and if I and then one has to try.
Right.
Right.
One should test with a small model to see whether the behavior they got is the same with the expected behavior, and then continue. Otherwise, while trying to increase the speed, you might end up decreasing the speed.
Right, right. And as you rightly said, Vedat, like when you think that you don't understand a component, try to try to do simple examples, like create a new model, just take the ideal gearbox and take an input and then just plot it, and then try
Right.
to see, is that what you expect? Right? Because
Mm,
many times when we use components from different libraries, we have no idea, right, how what the library developer thought, uh,
right.
what are the different mechanisms he has in his component. Right? The only way that we in our daily practice we do is we create small model, we simulate it, we check the parameters, and then we scale up. Right.
Exactly.
Right. Okay.
So it is a
So
common practice now and then you do modeling, right, Ankit? I mean, you start with small models and test it. When you are sure, then you continue to
yes.
integrate that model, the larger one.
So there
Another
is the
question,
question, Vedat, why again do we need the planetary gearbox in the first place? If you can again just brief
right,
about that.
right, Helmut. In this example, we just tried to show how we can simplify that high fidelity gearbox, including all the let's say stress related, vibration related dynamics. We just want to show how that thing can be simplified to another purpose with the essential variables only.
Right,
That's why we had to. But without using that, we could just set the equivalent gear ratio to the ideal gear, or maybe we could exclude the ideal gear, only use the planetary gear.
right.
So it is all up to
Right.
developers'
Uh,
way of
Also,
thinking.
I think the answer that you gave previously, Vedat, that um, this we are trying to mimic a real world gearbox which has a planetary gearbox, then a ideal gearbox attached to it. The reason, as you said, Vedat, before, that if you just use a single gearbox, right, then the transmission ratio that we need will be
Right.
very high. And when you have very high transmission ratio, perhaps the dimensions that you have become very big. Right? And when you have those big dimensions, you don't have that luxury of those big spaces. So you want to compact it. That is one. And I think there is also one reason which I am not sure, is also regarding the torque the ideal planetary gear can handle.
Right,
Uh,
that is for the high fidelity model, right?
okay,
But Helmut is asking why again do we need this planetary gear in that
okay,
model? So we were just simplifying that, right? I mean,
okay,
that thing, that is why we just want to each corresponding components to put.
right,
Uh, but
right,
yeah,
right. Then we have question. Sumi is asking, could you explain when we should use export FMU? Why? What is it that for? Uh, okay, so I have the link in the chat for the F or FMI page, but let me try to give an explanation again. So let's say we have our nice wind turbine model, right? And we have a friend to whom we want to send our wind turbine model to. And what they would do is they will just couple the wind speed, and they would try to model what is the power output from our model, right? So we want to share our model with someone else who is using a different modeling tool, right? Which can be Open Modelica, Simulink, or Simscape, or something else, right? Some different
right,
modeling tool, and you have created a model in System Modeler. So how can people using other modeling tool use your models? And so there is no language because we use Modelica language. Some other tool has their own proprietary language. How would those two models talk to each other? To make those sharing easy, there is a standard which is called FMI, which is functional mockup interface. So that is a standard uh, that is followed by a lot of tools. So what we do is we convert your model into that specific format, and some other tool can read that format and create the similar model in their tool itself, right? And vice versa. If someone else has created a model, let's say in Simulink, and you want to load it in System Modeler, they would export it as a FMI, and then you could import it in System Modeler. So that makes uh, 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 reuse of models or better, and you can share between multiple different tools, right? And in the link on FMI standard that we have posted, I guess, uh, you have nice videos, short videos on what is FMI, when should you use FMI, and then there is also perhaps a link to all the different tools that support FMI, right? So I would say reading through that page will give you a more comprehensive understanding about that tool. But primarily, it is used to share your models with other tools who don't use the Modelica language, right? Okay.
right.
Uh,
And also,
yes.
right, Selena says that the picture has gone. I don't get
Right.
which picture we lost.
Uh,
Other than that, yeah, John is saying that he opened the gear
right.
section of the rotating machinery library to find it.
Yes, and Shumi says it's just for reference, or you can simulate it. Sumi, you can actually simulate it in that simulation tool. So it's not only for reference, but they can simulate it. So what happens is they read the FMI format that your model is shipped with, and then they create components based on their tools. So they will take equivalent equations and they will recreate the component in their tool, which you can then simulate and use it as a component in that tool, right? So so yes, so when you share it, it is meant for simulation.
Right. Also, one question from Nicholas.
Mhm.
So Nicholas is asking whether it is possible to create a model, the dynamics of the drop test of a solid, of a known material and subsequent fragmentation of the solid. Yes, Nicholas. I mean, it is doable. So what you are referring is, I mean, in system modeler, what we use most of the time is like a lumped model. However, you can use finite element models as well. It is all up to what type of discretization you are creating in this system modeler. For instance, we can just go to the rotating machinery, Ankit.
Okay.
If we go to rotating machinery, over there we have, for instance, the beam component, which is like, let's say, longitudinal discretized finite element model. Or the yeah, we have like cantilever beam. We can just open that, the first one. That would work.
So
Yeah,
she opened
over there. Yeah. You open that. So here we see 10x over here, right?
it.
Ankit, can we go the upper? Yeah, here we see that we have the cantilever beam. When we click on that, so it shows what type of segmentation number we have, right?
Yeah.
So it says that we discretize this cantilever beam into 10 pieces. So similarly, you can just uh, create your own finite element model considering all each this component. That is, in theory, it is doable. Whether I have seen that type of example, no, but it is doable.
Vedat, what about the finite element thing? Um,
The integration thing,
here, or the can they use the finite element methodology or the finite element uh, tools available
right?
in Wolfram language to do that? The
Right.
gears.
In principle, when we say finite element analysis, it is like a PDE. But to solve it, what we do some discretization and change those PD to ODE. And in System Modeler, we solve the ODEs. So yes, in principle we do, and we have some blogs about that, how to do some kind of from Mathematica to System Modeler. You can create your PD model in System Mathematica and ship that model to with all dynamics to System Modeler, or other way around. You can have your system level modeling model in System Modeler and ship all those dynamic to Mathematica to get the boundary conditions for your PDE model, FEM model. So both directions is doable, it's possible. Uh, yeah,
Right. And John has a question that we only have a spur gear component inside the gears, right? It's not a package here. It's just a single component.
right. It's just a single component.
Yes. Yes. Vedat. And Vedat, you mentioned the nice things that you are currently exploring, right? You're
Right,
exploring how you can use the FEM analysis part in the Wolfram language. And once you
right.
do the analysis, how can you create a component from that analysis that you can integrate with your system models, right?
Exactly.
And also, I think you are working on a reverse workflow where you
Exactly.
use the system modeler model to generate the boundary conditions, and then you're using those boundary conditions in Wolfram language to get a better understanding with the FEM models.
Exactly. To get the holistic way of modeling, I would say, because sometimes, as I said, in like a finite element modeling, you need to go so many times back and forth to the iteration. Right, you have just a device level component. Let's say you are just applying some kind of force on the one component, which is maybe achieved by another engineer, and you got those boundary conditions, implement your device level, your component, and see how this look like. Then those results also should match. I mean, those effects, those deformation should be taken into account by the engineer who provided the boundary conditions. They
Right.
should converge to each other so that
Yes.
you can say, okay, everything is now converge and we have something working. So, but by using this approach, you have all the interaction, all the multi-domain modeling on the place already.
Yes. There is an interesting question, Vedat. How to export a selection of some of the variables? For example, let's say you just want to export a selection of sensors as results to Excel. I thought I remembered how to do it.
Oh, I don't remember what I will do. If I don't remember, I will go the Mathematica and use
Yeah.
simulation update. Yeah, over there,
Yes.
simulation data, and I will try to manipulate the output data over there.
Yes. Um, yes. Perhaps Sergio can add to that.
Yeah, I know. I was wondering also maybe you can export it to CSV, and then I'm not sure if Excel can handle CSV.
Yeah, it can, of course. Uh, yes. Um, I think I will get back to that tomorrow, I kind of think that there is a way of simulating specific variables to Excel. As Vedant rightly said, the easiest way for me to like the way I do it like is use the Wolfram language, where I would, I think we have covered this, Sergio, isn't it, in the second session? So if you can have a look at it on on the recordings of the second session, where we have used system model simulate, and we have
Right.
provided a list of the variables that we want to store, right? And we can then extract only those two value, only the selected variables in the Wolfram language, and then from there you can export it in any format that you want, right? That's the solution that I can think right away. I will talk to my developers. I think there was a way. Currently, if I try to do it, I am actually the current way I have to. I'm exporting all the variables. I will have a discussion and I will get back to it tomorrow. But the the solution that you can try right away is use system model simulate, provide the list of parameters that you want to store, and then use the result and export it as a Excel, right? And I would recommend watching the second day session where we have covered those aspects, and that might be helpful. Yes.
Right.
Okay.
And also, John is asking, yeah, John, one can change to a load right resistor and integrate its power loss. So it is doable. Right, Ankit? We can just see how much energy we are losing over a resistor in our model.
I Yes, I think so, John. Uh, I would need more details on exactly uh, what you're trying to do, but of course, you can integrate those losses from the load resistance and all. Um, right. Yep.
Right, we have a power sensor. We can just connect the resistor and then integrate the output of it and get the results, right, Ankit?
Yes. So for the resistor, I can use a heat port, goes to true, and we have the loss power, like whatever the losses that is happening from the resistor, we can extract from this red port that you could see here. And the equation is basically whatever the power you're losing, you are getting out from this red um, um, uh,
Port.
port.
Yeah.
So yes, you can get the power losses out of it. Okay. So just to summarize, Vedat, uh, we should use different models, and we should use models based on the modeling objective. Different type of modeling objective might need different type of models, and then we should try to understand what is the advantage and disadvantage or usefulness and limitations of different types of models. High fidelity models will be very slow. Low fidelity models will miss out some of the dynamics, and some cases with the business, some cases you don't even need those engineering equations. You can just think about it as systems, as flow of power and such, right? So it depends what we are trying to solve. And then um, it's like when you have a big model, try to break it into simple models and try to make sure that there is no interaction between the simple models. So rather than complicating your life, try to like trying to come up, instead of coming with one model that has everything, it's better to come up with several small models, right, which answers different queries,
Right.
because that way it is easier for you to troubleshoot and to understand all the dynamics. Sometimes we make a mistake of, okay, I will create this wind turbine model which will answer all my questions, but what we end up is slow models, very difficult to understand, very difficult to calibrate, very difficult to do uncertainty analysis. Rather, if you would have small models, we would have got more insights from it, right? And it would be easier for us to understand and for our model users to understand, right?
Right.
Okay, Vedat, I think we have again crossed our time limit.
Yeah, but
Uh,
we got so many questions. I mean, they were really nice questions, guys.
yes,
Thanks for the
yes.
questions.
Thanks a lot, guys, for your time. We are again apologizing for the delay. And if you have any questions, please feel free to to write us in the community, and we will be happy to answer. And Jan, I will also get back to your question. If you can select a list of variables from System Modeler itself, I will try to get back to that tomorrow. And tomorrow is a fun session. Tomorrow is a session where we will create music. We have one of our developers who creates analog synthesizers. He will be here tomorrow, and he will share some of his experiences. Right? Okay.
Yeah.
Thanks a lot for today. See you tomorrow. Bye bye.
Yeah. See you guys. Bye.